So this section is about precipitation and qualitative analysis. So what happens a lot of times is we mix two solutions together and we want to predict if those solutions will cause a precipitate. All right, so the way this works is we need to use our QK number line. Okay, so what happens is if we have our QK number line, so we have K, oopsies, come on, with KSP in the center. Oh, come on. There we go. And then we have Q on one side and we have Q on the other side. Just like before, if we use our QK number line, we compare our value of Q, which is the initial conditions, to our value of K, and we'll figure out which way the equilibrium has to shift in order to achieve, the system has to shift in order to achieve equilibrium. Okay, so the way this works is if Q is less than K, all right, if Q is less than K, which is this side, it's going to shift to the right. That means no precipitation. Okay, so the other option is Q is greater than K, it's going to have to go to the left. That means precipitate will form. Okay, so I'm going to show you how this works using this example. All right, so we're going to just go right through this and I'm going to spell it all out for you. And hopefully when we get to the end, you'll be all set with these kinds of problems. All right, so let's highlight the important information. Now, one of the things that students always say is they don't really understand what the equilibrium system is just from reading the problem. So the first thing I want to do is I'm just going to highlight this information right here. Our KSP is given for the compound CeIO3, cerium iodate. So that tells us what our equilibrium system is. So before I do anything else, before I read anything else, I'm going to write out my equilibrium system. We have CeIO3 solid. Remember these precipitation reactions, they have the solid on the left, yields reversibly, and then the ions on the right. Ce plus 3, aqueous, plus now we have 3 iodate ions. Minus 3, oopsies, that's a minus 1. That's why there's 3 of them. Aqueous. Okay, so first things first, we look at the KSP value. What compound do we have the KSP for? And that is our clue about what we're trying to find out. Okay, so we want to know the initial concentration of the selenium ions, cerium ions, and the initial concentration of the iodate ions in order to calculate Q. All right, but before we leave this, we're going to write our KSP expression. Don't ever do any of these problems without writing the equilibrium expression. Okay, so here it is. IO3 minus 1. Remember, you raise to the power of the coefficient. There's nothing in the denominator because the left side of the equilibrium is a solid. Okay, so we've got our stage set here for a Q versus K situation. All right, now let's go back to the problem and let's figure out what else we know. All right, we have 75 milliliters of the CeNO3. That's going to give us the Ce ions. Okay, and then the other thing we know is we have 300 milliliters of potassium iodate. That's going to give us our iodate ions. So the way we're going to do this is we need to figure out Q. And in order to figure out Q, we need to figure out what our initial concentrations are. Now, there's a couple things we need to do here is we need to figure out our initial concentration of the Ce ion. And that's going to be equal to the moles of the Ce plus 3 divided by the total volume of the mixture. Okay? And then we got to do the same thing for the iodate ion. I better plug her in after this video. Okay, we're going to do moles of the iodate and total volume. Those are the initial conditions. Okay, so what we're saying is that if we do this, we can plug that in and get our value of K. All right, so first thing we're going to do is figure out the easy thing. Let's figure out the total volume. So the total volume, when we mix everything together, is going to be equal to 300 milliliters, and it's plus 750 milliliters. And so we get 1,001.05 liters. Okay? So I guess I did two things at once. I'm sorry. I converted it to liters and added it. Let me step back. All right. Let's just do one thing at a time. 1,050 milliliters, and then I'm going to convert that to liters. 1.05 liters. Okay, so there's our total volume. So we got the bottom half of both of those equations done. All right, so let's highlight that. We'll come back to that number in a minute. Next thing we're going to do is we're going to figure out the number of moles, the moles of the CE. Now, moles is going to be equal to molarity times volume. So we know all of that. Okay, so the CE, the cerium nitrate, notice that the coefficient is 1 for this compound right here. So we can just use that information directly. We don't have to multiply it by the subscript because it's 1. All right, so we know the molarity, 4.00 times 10 to the negative 3. And we need to convert the volume to liters. So I'm going to multiply that by 0.75 liters. So my moles of CE plus 3 is going to be equal to 0.003 moles. So far, so good. We're doing great here. Now we're going to do the same thing for the next one. We're going to figure out the moles of the iodate ion. Okay, molarity times volume, and that's given in the problem. So the molarity is 2.00 times 10 to the negative third. Volume is 300 milliliters, so I'm going to convert that to liters. So the moles of the iodate ion, we have 0.006. Okay, so far so good. So now we have total volume, we have moles of each. So now all we need to do is go back and figure out our initial concentrations of both ions. All right, so we are almost done. Initial concentration of the CE ion is going to be moles of CE, 0.003, divided by the total volume, 1.05, which gives us a molarity of 0.00286. Our initial concentration of iodate, we take the moles of iodate, 0.006, divided by the total volume when we mix the solutions together, 1.05, and sorry, I'm ditching my units on you guys, moles. Okay, so what we end up with there is it's twice as much, okay, because 0.00571. All right, so we know that our initial concentration of CE is here and our initial concentration of iodate is here. So I should probably go back here and put in my little, oh, no, I want this one, initial symbol. Okay, those are not equilibrium concentrations, those are initial concentrations. So now I can plug them into my equilibrium expression and get my value of Q, because Q is going to be equal to the CE plus 3 initial concentration times the iodate. We're using initial concentrations, but in the same way as the KSP. All right, so we have 0.00286 and 0.00571 cubed. Okay, don't forget we have to raise to the power of the coefficient. So our Q value in this case is going to give us, all right, 5.324 times 10 to the negative 10. So now I can do my QK number line. So here it is, K, Q, Q. Well, let's figure out which one it is. Our K value is given in the problem as 1.9 times 10 to the negative 10. And our Q, our K, this is our KSP. We can be fancy and call this QSP if you want to. And our Q is bigger than K, 5.324 times 10 to the negative 10. All right, so we're comparing these two numbers, and so what that means is Q is bigger than K, so the equilibrium is going to shift to the left. The system has to go to the left to reach equilibrium. If it goes to the left, then we can say with definitively, yes, a precipitate will form. So, okay, system has to move left to reach equilibrium. And remember what I said at the very beginning? If the system has to go to the left, if our system is going left, that means it's going to form the solid. So in this case, since Q is larger than K, it's going to go to the left. We're going to get a solid. All right, that's it for that. Let's try this next example. So this one starts off just like the other one, okay? And then we've got to take that information a little bit farther. Okay, so the first thing I want you to do, as always, is we want to look and see what is the KSP value for, okay? So our KSP is for magnesium phosphide. So that is really important because we need to use that as sort of our beginning part of the problem. So before I go any farther, before I even read the rest of the problem, I'm going to do this. Magnesium. Okay, so I'm going to write my equilibrium expression so I can make sure I know what I'm where I'm headed here. And KSP is equal to mg plus 2 times F minus squared. Okay, so the first thing we want to do is we got to first figure out whether we're going to get a precipitate or not. Okay, so the question is, when we mix these two solutions together, what are the concentrations of the magnesium and the phosphorus ions? The phosphide ions. So what happens here is we got to first do our QK number line, because if a precipitate forms or a precipitate doesn't form, that changes the outcome. All right, so I'm going to start off where I was on the last problem. First thing I'm going to do, let's just do total volume. Okay, total volume is going to be 150 milliliters plus 250 milliliters. Okay, so the total volume, 400 milliliters, which is 0.4 liters. Okay, and I want to figure out the moles of magnesium. Okay. All right, so if I'm going to get the moles of magnesium, I need to do molarity times volume for the magnesium solution. Now, in this case, the magnesium comes from the magnesium nitrate. Okay, so we know we have 0.15 liters times the molarity, which is 1 times 10 to the negative second. All right, so our moles of Mg is 0.0015. That's the moles of the magnesium ion. Okay, now we're going to do the same thing for the fluoride ion. Okay, molarity times volume for the fluoride gives us, let's see here, we have 1.0 times 10 to the negative 1 for molarity. And we have volume is 0.25 liters. Okay, so for moles of the fluoride ion, we get 0.0250 moles. Okay, now we're going to go ahead and figure out our initial concentration of magnesium. And that's going to be the moles of magnesium divided by the total volume. Okay. Right, divided by total volume. So that is 0.0015, and our total volume in this case was 0.4. Okay, so our initial conditions, our initial concentration of the magnesium ion, where are you? 0.00375. Now I'm going to do the same thing for the fluoride ion. Moles of F minus is equal to 0.0250. And I'm going to divide that by, let's just fill in the units so you can follow what I'm doing here. The total volume in liters, and I get 0.0625 molar. Okay, so with our initial conditions, we're going to plug that into our equilibrium expression and calculate Q. So Q is going to be equal to, what do we got here? 0.00375, our initial concentration of magnesium, times 0.0625 squared. So Q equals 1.46 times 10 to the negative 5. Now I'm going to use my QK number line. Hi, sweetie. The dog just came in. 6.4 times 10 to the negative 9 is our K value. And our Q was 1.46 times 10 to the negative 5. Okay, so what that tells us is our Q is greater than K. So it's equilibrium is gonna have to move to the left. I mean, the system goes to the left to get the equilibrium. So, so it will precipitate, will form. All right, so far so good. We've done basically what we did in the first example. All right, so we did the total volume, the moles of each ion, then we calculated the initial concentration of the two ions in question that are in our equilibrium system. Plug those in to solve for Q, and then do the QK number line. All right, now the question is asking us, if we go back to the original question, what we want to know is the concentration of magnesium and fluorine at equilibrium. All right, so what we need to do first is we need to do a little tiny stoichiometry question, okay? So see here we have this before, change, and after. So when we mix these ions together, it's going to give us a precipitate. So we're going to use the stoichiometry to figure out how much precipitate we get, all right? So here we have our magnesium ion, and we have 2 times the fluorine ion, and that's going to give us our magnesium fluoride precipitate, okay? So we'll go back to our moles, okay? So we know that we started with 0.15 moles of magnesium and 0.025 moles of fluoride, okay? So I'm going to put that in as my before. 0.015 and 0.0250. Okay, so the magnesium is going to be our limiting reactant here because it's so much smaller. So the magnesium is going to go down by 0.0015. If all of that is consumed, then the fluorine is going to go down by a ratio of 1 to 2. So it's going to go down by 0.0030. So after the precipitate forms and after this stoichiometric relationship is all done, we have 0.022 moles of our F minus left over. Okay, so when the precipitate forms, we have a solution and it contains fluoride ions and it has that solid magnesium fluoride at the bottom. Okay, so now we're going to get our equilibrium system set up. So we have one more phase to do. All right, so first phase was Q versus K. Second phase, stoichiometry. Now we're going to do an ice chart and figure out our equilibrium conditions. Okay, so here's our equilibrium system. Magnesium fluoride yields reversibly the magnesium ion plus 2 times the fluoride ion. Okay, now our initial conditions, we have none of the magnesium. That's all used up in our stoichiometric thing. Our fluorine, we have 0.022 moles divided by the total volume, because remember we mixed everything together. The total volume was 0.4. Okay, so our initial conditions of the F minus, backside of my cheat sheet, is going to be 0.055 molar. Okay, so in our ice chart, just like usual, we have our initial conditions. Now we're going to do it in terms of X. So when this reaches equilibrium, we're going to go minus X and minus 2X. So at equilibrium, our concentration of magnesium is going to be X, and our concentration of the fluoride ion is 0.055 minus 2X, which we can approximate as 0.055 because the KSP is so small. Okay, 10 to the negative 9. All right, we're almost home here. So we're going to plug this into our equilibrium expression. We know that our equilibrium expression is KSP is equal to mg plus 2 times F minus squared. Okay, so KSP is 6.4 times 10 to the negative 9. Our magnesium concentration is X. Okay, and our fluoride ion concentration is 0.055 squared. All right, so if we solve for X, that tells us the concentration of the magnesium at equilibrium. In this case, X is equal to 2.1 times 10 to the negative 6 molar. Okay, so that tells us that at equilibrium, our magnesium ion concentration equals X, which is equal to 2.1 times 10 to the negative 6 molar. And our fluoride ion concentration is equal to, really hasn't changed. I mean, we could do the math. We could subtract 2X, but that's just going to be within significant figures. Look at how small that is, 2.1 times 10 to the negative 6. You can see why we can approximate that. Okay, that was a doozy, wasn't it? There's a lot of parts to that problem, okay? This problem kind of pulls together so many different things that we've learned, okay? All right, that's it for that one. The last example in this section is called selective precipitation. So what happens here is you have a solution that contains 2 metal ions. And then you add to it an anion to see, and it's going to cause precipitation to occur. And the question is, which metal ion is going to precipitate first? All right, so we're going to work through this example to show you how this works. So we have a solution. Oh, sorry, the first example is just an example. So typical scenario, like you would have a barium and a silver ions in solution. And we know, if you remember back to our solubility chart days, those were always in the exceptions rule where things precipitate out, okay? If we add NaCl, when we add NaCl, what we're adding is the chloride ion. So the question is the barium chloride going to precipitate first, or is the silver chloride going to precipitate first? Now, in this case, it's going to be the silver chloride that goes first, leaving the barium still in solution. So as you can imagine, we have to use the KSP values in our equilibrium systems to figure this out. All right, so here's our example. In this example, we have two metals in solution. We have copper metal and we have lead. Okay, so here's our initial concentration of the copper. Okay, and here is our initial concentration of the lead. So the question is, we are going to be adding iodide ions gradually. Now, like I said in the previous examples, what's going to determine your problem is this. Notice that we're given the KSP for lead iodide and we're given the KSP for copper iodide. So if you don't know where to start, that's where you start. Okay, so first thing we're going to do is just write our two equilibrium expressions. So we have lead iodide yields reversibly lead plus iodide. Okay, and we have our KSP expression is, let's not forget to write the KSP expression, PB plus 2 and I minus squared. Why did I write a squared there? Sorry, that should be minus 1. Okay. So there's half of our system. Now the other half is going to be from the copper, okay? So we're going to write our copper equilibrium system, copper iodide, Cu plus, that's a copper 1 iodide, okay? Plus I minus, and here's our KSP expression, Cu and I minus. Okay, so the question is, which one's going to precipitate first and how much do we need? So the way we're going to do this is we are going to calculate the iodide ion concentration necessary in both of these systems. So essentially we're going to be doing two separate calculations here, okay? So I'm going to do my ice chart here, ICE for the, you know what I'm talking about, the lead. Okay, so PbI2 yield reversibly, Pb plus 2 I minus. Okay, now we already have the Pb in solution, right? Remember that's a solid, so who cares? Pb is 2.0 times 10 to the negative 3. Those are our initial conditions. Okay, we don't have any I initially, so we need to figure out how much we need to add into our system. So we're going to go plus x. So at equilibrium, we have our x is negligible times 10 to the negative third, and we have x. Okay, so let's just finish this out with this side, and then we'll do the other side. Let's plug in what we know. We know the KSP for PbI2 is 1.4 times 10 to the negative 8. And we know the Pb concentration, 2.0 times 10 to the negative 3. And we know I is x squared. Oh, I'm sorry, that should be 2x squared. Boop. Okay, now what we need to do is solve for x. Okay, so we're going to do a little math here. So we have 1.4 times 10 to the negative 8. Okay. I'm sorry, I don't have the answer done up. Let's do it real quick. So then we're going to divide that by 2.0. Times 10 to the negative third. Then I'm going to divide that by 4. And then I'm going to take the square root. All right. Dun, da, da, x, in this case, is equal to 0.0013. All right. So now I'm going to do the same thing for the copper. So remember that x is equal to my I minus concentration. So I'm going to do the same thing on the other side with the copper. So we've got a separate little problem to do here. All right, so here's our ice chart. CuI yields reversibly. Cu plus plus I minus. Who cares? You're a solid. Okay, our initial concentration of Cu is 1.0 times 10 to the negative 4. I is 0. Okay, we're going to do plus x plus x. All right, 1.0 times 10 to the negative 4 and x at equilibrium. So let's plug that into our KSP expression. We have 5.3 times 10 to the negative 12 equals 1.0 times 10 to the negative 4 times x. Okay, so when we solve for x, this time we get 5.3 times 10 to the negative 8. That one I had already done. All right, remember that's the I minus concentration for this side of the equation. So here's our answer. Ta-da! We're going to compare these two numbers. So the one that requires the least amount of I minus is the one that's going to precipitate first. All right, so in this case, the copper 1 iodide is going to precipitate first because it's going to go when you've only added 5.3 times 10 to the negative 8 molar of the iodine concentration. Okay, so really, essentially, this problem is really just solving for x, and the one with the smaller x is the winner. All right, so let's write that in here. So, oopsies, not in highlighter. CuI precipitates first. Because I'll go ahead and write it out. It requires a lower I minus concentration to form a solid. Okay, ta-da! That's the last example for this section.